Let's find a basis for the space of alternating covariant k-tensors. Now, as usual, we have to ask, so we want to describe this basis, but in terms of what? Of course, it will be in terms of the basis of V. And so if V has a basis, E1, En, then we have a dual basis, V1, Vn. And remember to be careful about the position of the indices. Now, since the k-tensors are generated by tensors of this form, we are just taking tensor product of any k elements in this. Then you know that then this space must at least be spanned by tensor of this form. So this is a good spanning set. Now we just need to trim it down a bit to get independence. First, observe that when we interchange the order of any of these covectors, we get a covector in the same span. Note that here, because this is one covector and this is one covector, the sign here must be minus. The same argument works when you are interchanging two covectors here inside this big wedge. So all the permutation of these indices I1, Ik just give us vector in the same span. Thus, the first step in reducing redundancy is to fix an ordering of these indices. Now observe also that there cannot be any repetition. If there is any repetition, then the covector, the whole tensor, must be 0. So why is that? Well, let's just look at the case of one covector wedged with itself. By anti-commutativity, we know that it must be equal to its own additive inverse, so it must be 0. Thus, we can further cutting down the index here, so we should have no repetition. Turns out, this is good enough. There is no more redundancy. This actually gives a basis. So let's see why. For convenience, let us denote this by phi I. So I stand for a set of indices. To show algebraic independence, we will suppose that we have the following linear combination of these phi I equal to 0. We want to show that these coefficients are gonna be 0. The idea is we want to somehow be able to pick out this coefficient. What we will do is that we will apply both sides of this to Ej. That means a wedge product of k elements here. It turns out that all of these are gonna be 0 except when the indices actually match, in which case it's gonna be 1. So this is really the delta function. Thus, this means that the only coefficient that survives is Cj, right? And we have that Cj must be equal to 1. So that shows linear independence, and thus we have an explicit description of a basis of this space. Now then, what can you say about its dimension? What is its dimension? Now, choosing a basis corresponds to choosing k distinct elements from here. So the dimension of this space just corresponds to the number of such choices. In particular, you see that if k is n, then this space is one-dimensional. And if k is bigger than n, then we have no tensors. Okay, but in the proof though, we left out some points. How do we know that this is going to be equal to delta ij? How do we compute this? Well, in the next video, we're going to discuss how to compute wedge products of one covectors in general. And that will answer this question.